In section 6.3, we'll be discussing Riemann sums with sigma notation. So in the last section, we approximated the area of a region by cutting it into simple shapes such as rectangles or trapezoids, finding the area of each of those shapes, and then adding them together. Sometimes our calculations might get tedious, especially if we get smaller and smaller intervals. So there's a simpler way to actually write that, and that's using sigma notation. You may or may not have seen this notation before, so I just wanted to review it before we go on to the calculus part. So this is a sigma. It stands for a sum. So whenever I see this symbol, the capital sigma, the Greek letter, it means I'm going to add things together. The summand is this 3k plus 1. It kind of acts like our function. We'll have our variable part there at k. Sometimes you'll see it as an I or a j or an n. That's your variable, our lower limit and our upper limit. So those limits are similar to what we have with integrals. What this means is I'll first plug in 2, 3 times 2 plus 1. Then I'm going to add that together with 3 times, I'm going to go up by an integer, 3 times 3 plus 1, plus, then I'll do 3 times 4 plus 1, and then finally I'll do 3 times 5 plus 1. Then I would find that sum and calculate. So it'll be important for you to understand both summation notation and then how to translate that into sigma notation and vice versa. So here I have 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. So I could rewrite that as my sum from k equals 1 to 5. Those are the numbers I'm plugging in. And the function I'm plugging it into is k squared. Now, there's more than one way I could have written that. I could have started at 0 and then added 1 each time or something like that, but this is usually the simplest function to start out with. Here I see I'm looking for my integers changing, 3, 4, 5, 6, 7. Those are all in the denominator. My 1s are staying the same. So it appears that I start at 3 and I stop at 7 and I'm plugging into 1 over k. So I'm just looking at how those individual terms change. Now in the third problem, I have a sigma notation, the sum from j equals 0 to 5 of 2 to the j. So I'm just going to plug in 2 to the 0 plus 2 to the first plus 2 squared plus 2 cubed plus 2 to the fourth plus 2 to the fifth. Okay. The last one, we have a sub 2, this is called a subscript, so a sub 2 plus a sub 3 plus a sub 4, etc. And so I can write that. I can choose whatever letter I want, so let's call it n. N equals 2 up to 7, and it's a sub n, just some subscript. Let's practice some more. Let's write this summation denoted by these sigma notations. So here we have k cubed, and we're going from k equals 1 to k equals 5. So 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed. We're not actually going to worry about calculating these. We just want to kind of write them out. In part B, we have something that's a little bit different. We have negative 1 to the j. Negative 1 to the j is called an alternator. That's going to actually make your sign alternate. So when I have negative 1 squared, that will be positive. But once I have a negative value there, negative 1 cubed, sorry, not negative, an odd value. Negative 1 cubed is going to give me a negative 1. So my sign is going to alternate back and forth. So my first value will be positive 1 over 2. My next value will be negative 1 over 3, plus 1 over 4, minus 1 over 5, plus 1 over 6, minus 1 over 7. And sometimes we'll have a bigger expression that we need to plug into, like 2m plus 1. So each time there, I'll do 2 times 0 plus 1, plus 2 times 4 plus 1, plus 2, sorry, not 2 plus 4, I was getting ahead of myself. That should be 2 times 1 plus 1. 2 times 2 plus 1, 2 times 3 plus 1, and then we'll end with 2 times 4 plus 1. Make sure you have sums in between each of those. So this was all just review. Let's get to the calculus now. So we're going to evaluate the sums of the areas and write the sum using sigma notation. So I notice here that my function is given to me, it's y equals 1 over x, so I will be able to find those values, even though it might be hard for me to see on the graph. So I can see that my base for each rectangle is 1. My height here is at f of 3. And so I'm going to plug 3 into 1 over x to get my y value there. So I have 1 times 1 over 3 plus my next rectangle has a base of 1 as well. My height is f of 4, so 1/4, plus 1 times f of 5, so 1/5. So the way I'm going to write that in summation notation, just like we did before, my sum from k equals, I start at 3 and end at 5. And then I'm plugging it into essentially 1 over k. I could write it as 1 times 1 over k, but I can also just write it as 1 over k. And that would give me the area for just this approximation. Now let's do a left-hand sum instead, still 1 over x. My width is still 1 for each of these. So I have 1, my first height is f of 1, so 1 over 1, plus 1 times 1 over 2, plus 1 times 1 over 3, plus 1 times 1 over 4. Don't get carried away and add plus 1 times 1 over 5. Our last rectangle right here stops at a height of 1 over 4. So our summation here is the sum from k equals 1 to 4 of 1 over x. Not 1 over x. I apologize. I'm used to writing 1 over x because that's our function. It's 1 over k. All right, now C looks a little bit more complicated. It's just some general function f of x, some general terms here. And so we still have to remember that our area is equal to our base times our height. And so for my first rectangle, my base is going to be, I would have to find the distance between those two values. So x sub 1 minus x sub 0. My height is whatever f is at this value, x sub 1. So times f of x sub 1. Plus, now my next rectangle, I find my base from x sub 2 minus x sub 1. And then I'm going to multiply that by the height at x sub 2, f of x sub 2. My last one, same idea. I'll have x sub 3 minus x sub 2. My height is at f of x sub 3. So let's see if we notice any patterns that might help us generate our formula in sigma notation. So x sub 1 minus x sub 0, x sub 2 minus x sub 1, x sub 3 minus x sub 2. I notice that those are all 1 apart. I also notice that this term, my first one, x sub 1, is where I evaluate my function. X sub 2 is f of x sub 2, x sub 3, f of x sub 3. So that might help me out there. So there's multiple ways that you can write this. I'm going to start at 1, because that makes more sense to me, and go to 3. So my numbers here, my index, is going to match up with this first term, or with my height term. So I'm going to go from k equals 1 to 3. Then I'll have x sub k for my first value, x sub 1, x sub 2, x sub 3, minus x sub, so if I want to get 0 here from 1, I would have to subtract 1. So this is k minus 1 for my subscript there. Same thing for my next term, x sub 2. If I subtract 1 from that subscript, I would get x sub 1. And then my height is times f of x sub k. So that idea is going to help us generalize for a Riemann sum that has more than just 3 rectangles. What if we had infinitely many rectangles, or some number of rectangles? What would that look like? So remember that the Riemann sum is the total of the areas of these rectangular regions and is an approximation of the area between the graph of f and the x-axis. A reminder that n is our number of rectangles. To find our width, delta x, we do b minus a over n. And our height will be our function at some x value, x sub I. And so you can use k's or i's. I think maybe I should use k's there. We've been using k's, I'll use k's. Sorry, let me fix that. So what I want to think about is my delta x is my width there, and my height will be the f of x. Right. If I'm doing, this is going to be a right Riemann sum in this picture. F of x sub 1, f of x sub 2, and then going on all the way until I get to f of x sub n. Notice that those are 1 less than it each time before that. Notice I start at A, end at B, etc. So in sigma notation, the way I'm going to write this is my sum from k equals 1 to n. So notice I have n is my number of rectangles. So my first rectangle up through my nth rectangle. My base is delta x. My height is f of x sub k. However, I'm going to actually change that order just to help us recognize a formula. This is f of x sub k times my delta x. So once again, this is my height at x sub k, and this is my width. Now sometimes our delta x is variable, like in the last example. Other times it's consistently the same width. So in this picture it seems to be the same width. Usually in these problems we will assume that we have equal subintervals, which will help us out. So what we want to think about is how could we actually get a better approximation of the area under a curve. So we've used some number of approximations, some number of rectangles here, but with more and more rectangles, the approximation of our area will become more accurate. So the more rectangles we use, the more accurate our approximation will be. So that means our n is approaching infinity. So this gives us sigma notation. If we're thinking about something approaching infinity, we're actually going to add a limit to it, and this will actually tell us the exact area underneath a curve. So our integral from a to b, this is exact area under the curve. Our Riemann sum was an approximation. If we take a limit of our approximations, we will get the exact value. So we're going to say the limit as n approaches infinity of the sum from k equals 1 to n of f of, now I'm going to start at a. This is a little bit different than up here, just because of the way I have it written. A plus delta x times k, some number of delta x's, and then times my delta x. So f of a plus delta x times k, that's what generates these. So if I start at a and add 2 delta x's, I get x sub 2. If I start at a and add 1 delta x, I get x sub 1. Sometimes you'll see this index start at 0 instead of 1, and that usually indicates a left-hand sum instead of a right-hand sum. You don't have to worry too much about that. So this looks like a crazy complicated formula, but what you'll see is we're just going to use it to rewrite some integrals in this sigma notation and also the other way around. Let's try one out. Okay, so we're going to start with the integral from 3 to 5 of 4x dx. We're not actually calculating this integral. We're just going to express it as the limit of a Riemann sum. So the things that we need to know are our delta x, that's going to be important. We find this the same way we did with our other Riemann sums. So I do top minus bottom bound divided by n. I don't know what n is in this case though. I don't know my number of subintervals. And so this is just 2 divided by n. And so when I'm writing my integral, I'm going to do the limit as n approaches infinity of the sum of k from k equals 1 to n. That part stays the same. Then I need to think about what my f of x is. My function f of x is 4x. And I want you to pay close attention to that x part. Wherever there is an x, that's where I'm going to plug this stuff in. This is taking the place of my x in my function. So I'm going to have 4 times something, because my function was 4x. That something is going to be, I'm going to start with a, which is 3, my first value, plus my delta x, which was 2 over n, times k, and then I have to multiply that by a delta x. The way I remember the delta x is in my integral I have a dx. That is the delta x there. Okay. Now sometimes you'll see that written instead, just a little bit of a tweak here. 4 times 3 plus 2k over n times 2 over n, or you might even see the 4 times 2 over n simplified as 8 over n, and you might have to just match up your answers that way. In part B, we have the integral from 2 to 7 of the square root of x squared plus 1 dx. So again, we're going to take our delta x, 7 minus 2 divided by n, that gives us 5 over n. So find your delta x first. Now we'll write out our limit notation. Limit as n approaches infinity of k equals 1 to n. Now write out your function, square root of something squared plus 1, and then we'll have our delta x. Now that something in this case, we want to think about what that is. That something is going to be my a, looking back up at the formula, a is 2 plus 5 over n, my delta x, times k. So I'm going to write that as 5k over n. And then outside of my function, notice outside my radical, going to multiply again by delta x, which is 5 over n. Last one, part C, we're going to calculate our delta x again. We have the integral from 1 to 6 here. So 6 minus 1 over n is 5 over n. So we'll take the limit as n approaches infinity of the sum of k equals 1 to n. Now, again, I'm going to rewrite my function, natural log of 5 times something. Leave the something there, minus 3. That something is what you're filling in. So instead of x, I start with my a, 1, plus 5 over n times k. Then I'm going to multiply that whole thing by 5 over n, by my delta x. Don't forget that delta x at the end.